We're just really pleased to be here to share with you what we've been thinking about in terms of supporting students who are underrepresented in the sciences. And I'll be co-presenting with Erin Palmer, who is a graduate student in science and math education. She's writing her thesis on this work. And Dr. Sabriya Rosemond, who got her PhD here in molecular and cell biology, and then is doing a postdoc as part of this project. And we're hoping that we can engage you in a conversation about how to design equitable undergraduate courses. You're going to hear that word equity a lot. So the story that we want to try to tell you today is how we began to question inequitable hierarchies within our science courses, and how we set about to redesign a practice-based classroom system for Chem 1A. Okay? So we're going to talk about how we got there, who came to us, and how we were thinking about these inequities. And then we want to talk about the principles behind the classroom design. We're going to engage you in a lesson, an abbreviated lesson, because we just want to give you a sense of what we're actually doing in our classroom. And then we want to describe how these activities have socialized the students into new ways of seeing and participating in science. Okay, we'll go over that in more detail. We'll show how the data we collected indicates that we are disrupting these cycles of inequity in our classrooms. And then we're going to end with a conversation of how we might collectively work together to ensure that we offer students a rich, connected, and relevant understanding of science, and we recognize the various ways in which these students are brilliant. Okay? I use that word on purpose. All right, so to begin, I'm going to ask you to introduce yourself to somebody that you don't know, and I want you just in a very quick share, what does an equitable classroom mean to you? Okay, so just a quick introduce yourself to someone. Okay, let's get back together. Oh, but yeah. All right, so just in a couple of really quick statements, what are some of the things that you talked about? Just a really short phrase from different people. Go ahead.
Sense of belonging.
Sense of belonging. What else? Go ahead.
A lack of assumptions.
Oh, lack of assumptions. What else? Nobody has anything else? Yep. Go ahead, Rudy.
A place where you don't have to feel like you have to represent your entire population or group.
Did everyone hear that? That you're not representing your entire population as the single student in the class. Did you have one that you were?
I'm going to share my partners.
Okay.
And I think it's being valued actually for your unique contributions.
So being valued for your unique contributions. Go ahead.
Not feeling like you have something to prove to be taken seriously.
Not feeling you have something to prove to be taken seriously. I take it many of you have been talking to students who actually feel this way. Go ahead.
Again, my partner had a great one of giving every student the tools to succeed with the learning objectives.
Yeah, giving every student the tools to succeed. All right. So that's a great start. That's what we want to talk about, the ways in which our classrooms are and are not achieving all these wonderful statements that you just made. So I'm going to turn it over to Erin, who is going to lead you through the first part of the talk.
Great. So we started by thinking about equity at the classroom level because we are making this claim that what is happening in our classrooms is related to these larger disparities and attrition out of STEM majors. So if we look at 4-year and 5-year completion rates, there are disparities between our underrepresented minority students and their white and Asian counterparts. And we know that this is happening in particular in the first 2 years of STEM majors when students are taking these large introductory courses. And this is true for us in Chem 1A, which is the first semester chemistry class for non-chemistry majors. So it's engineering majors, life science majors, pre-health majors. And back in 2012, the Office of Multicultural Student Development came to us with concerns about how many Black students were taking Chem 1A and then switching their STEM majors after that course. And specifically, what students were saying is that they were questioning their ability to succeed in the sciences after this one semester course. And this was striking because this was my first year of graduate school. I was mentoring a really talented young Black woman in the class. 3 weeks into the class, she took her first midterm, got a pretty low score, and texted me, I'm going to drop the class, I think science isn't for me, like I just don't feel smart enough to continue. And while there's so many things we could say about that, what struck me is how sensible it was for her to connect this grade to her overall smartness, and then smartness to her fitness for the sciences, right? How quickly that happened for her. And that led me to wonder, as an early graduate student, what are the messages about smartness and about race and about science that are available in the world that students are tapping into as they make sense of themselves in relationship to science? So we carried out interviews, we carried out focus groups, and we turned to the literature. And what we came to is that there are very narrow narratives about scientific brilliance that exclude most of our students. And I'm going to talk about that in 3 ways. The first is that STEM is perceived as this high status field, right? It's historically pursued by the intellectual elite, and there's a belief that it takes an innate talent or an innate kind of brilliance to be successful in science. And that's problematic because brilliance is a racialized and a gendered construct. There's a lot of research in the education literature that shows that storylines or narratives that connect race and to ability in science, things like Asians are good at science, create these hierarchies of perceived ability that position our Black and brown students at the bottom, our Asian students at the top, and our white students sitting there as that invisible norm. And in interviews, all of our students are very aware of these storylines, and our Black and brown students in particular have to contend with them in a different kind of way, right? They might be experiencing, or they told us, that they're experiencing racial microaggressions about their perceived lack of competence. And so in addition to these narrow views about kind of who counts or who can do science, smartness or goodness at science is constructed really narrowly. We're socialized to see smartness as knowing lots of information, right? Solving problems effortlessly, getting a lot of correct answers. And so smartness is kind of constructed in ways that make it feel really scarce. And while these messages aren't necessarily getting produced in our classes, they exist in the world, and our classes are designed in ways that make them easily available for students as kind of sense-making tools. So one thing we asked students about in interviews was their perceptions of this class, right? How is this class kind of allowing you to tap into these ideas about smartness? And the idea that chemistry or Chem 1A is a weeder or a weed-out class came out a lot. And that might sound like a common phrase you've heard that's maybe benign, but for students, when we probed their sense-making, this was a narrative about sorting by ability, that this class is designed to show them whether they are part of the weeds that don't belong in science or part of this up-and-coming crop of scientists, right, who have the ability to be successful. And that affects then how they read the interactions they have in the class, how they read their performance. So you get a low score, all of a sudden, you're extrapolating to your belonging in science and your smartness, as opposed to thinking, oh, maybe I didn't study in the right way, or maybe this test just didn't really show what I knew. And aspects of the design kind of perpetuate these ideas about smartness and weed out course, right? Things like the high competition that exists in these large classes, the fast pace that they move, the wide breadth of content, right? Taps into ideas about knowing lots of information. There's an over-reliance on academic jargon, right? That makes you feel like, oh, to be smart is to be able to use these big complicated words. And the positioning of students in relationship to kind of this expert knower at the front of the room or the sage on the stage all kind of contribute to this. And then maybe at the crux of the problem is that the way that we're teaching science in these kind of large lecture classes frames science as what I'm going to call school science, as a discrete body of facts that are kind of available to be memorized, that it's static, right? What we're learning is truth. And a lot of the learning is individualized, where if we look at science as a social practice, it's a developing explanatory models. It's actually a diverse set of sense-making practices to make sense of the world. It's iterative, it's really messy, there's often a lot of failure involved, it's creative, and it includes a lot of collective sense-making. And so this stuff that's sitting here in the green box is really what we want to engage our students in. This is the learning that we're trying to support, And we also feel that it has the potential to offer more inclusive meanings about what it means to be good at science. So this framing of the problem led us to ask 3 years ago, what does it look like? How do we redesign our whole classroom system in order to disrupt these current systems of inequity? And as Angy mentioned in the opening, we settled on this big goal, which is that we need to socialize students into new ways of seeing and understanding what science is, and we're going to do that by supporting them to participate in actual science, right, in the practices of science, to make sense. And we're doing that such that they're engaged in rigorous chemistry learning, right? They're developing a rich, connected understanding of chemistry, and we're trying to support them to recognize the various ways in which they're already brilliant and then develop those tools that they're bringing. So how do we do that? We have this kind of goal that we're aiming toward. We had to think about what are the conjectures that we're making about design that are going to get us there? What kind of principles are we going to organize our design around? And the first one was, if we want students doing science, engaged in the practices of science, we have to figure out for ourselves what is the rich chemistry that's there to be discussed or to be thought about. And to get there, we have to organize our entire curriculum around the central ideas in chemistry. So it was one place we started. It was just reworking curriculum. And then when students come to us in class, what we want them doing is being engaged in collective investigation of chemical phenomena to build understandings about and explanations about properties and behavior of matter, right? This is what chemists do. So we want to engage students in doing that when they're with us in class. But to do that is risky. It's really different than what they're used to doing in traditional lecture courses. And so part of what we need to do alongside of supporting that is reframe for them what science is about and what counts as brilliant. What is brilliant scientific work? We need to do that in ways that are expansive and more inclusive and authentic to actual science. So I'm going to hand this to Angy.
I'm okay. The clicker. I got this. All right. So just very briefly, Chem 1A is a prerequisite, as many of you know, for many majors, almost all of the pre-health majors, environmental science, biological sciences, and many of the engineering disciplines. It's typically taught in 3 large lecture sections of up to 500 students sitting there, and as you look around, you may not see anyone who looks like you. And even though there are many students, many of our students are shy and they don't make substantial connections in that situation. So what we did was created section 4. We did that on purpose. It is the 4th section of the same class, all right? It is not remedial. It is not a different class. It is a different way to teach the same material. We chose on purpose students who had less than 1 year of high school chemistry. That's a proxy for being in a school that didn't offer a lot of AP classes. We took anyone who was repeating the class, and we made lots of great connections with staff around campus who advised students, EOP, Summer Bridge, the engineering prep students, and really invited them in to this. The classroom is set up differently. This is my...
So I know we put EOP on there, but it's not defined.
Oh, yes, please.
My name is Mitzi. I'm the assistant director for EOP. And I just wanted to find that EOP is students that are first generation, low income, and or underrepresented, just to kind of give more context to that slide.
Thank you, Mitzi. Yeah. I got so used to the acronym that I forgot to explain it. So we're really reaching out to a lot of the wonderful support staff for students who are coming into the university as first generation, low income, and we really tried to target students of color as well because they feel very isolated in this large class. So anyway, this is Moffitt 145. It's got these movable tables. I didn't know whether we could pull this off or not, but we had over 100 students working in teams of 4. I thought it might get too noisy, but it didn't. You'll see a video later. And we had a multi-tiered instructional staff. We had me as the instructor. I had 2 GSIs, and in the section that, not this year, but last year, we had the 2 researchers involved. And we also have these wonderful undergraduates who've already taken the class. they take a class to learn about teaching and learning, and then they came in and helped. So I had about 8 of them, and they're wonderful. So we have a multi-tiered instructional staff that's rotating around. Okay, so now what we're going to do is oh, sorry, go ahead.
You said that the teacher scholars took a class on teaching and learning?
Yes. Chemistry department, and they have over 100 students taking that class every semester. They are largely not chemistry majors. They are very often biology majors or engineers, anyone who's taken the class, right? And then they're often assigned to the lab, and we've got a lot of research on that where it's really making a difference for the students, for the GSIs, to have another person in the room helping. And so these undergrads, they were just spectacular. And
the students that take that class, they don't all teach the chemistry course, or they were not all the teachers, scholars?
No, so they're distributed among all of our lower division classes. So they could be in the organic chemistry labs or lectures or discussions, Chem 1A lab. And so it's been a highly successful program because the students also get to know each other and they feel part of something after they've completed the course. And I encourage any student, I'm not looking for only the A+ students because they get so much out of trying to help assist in this group work. So, yeah.
And how are the undergraduates paid? Are they paid out of your
No. It's a class that they take. And so they are not paid. This is just, they don't do any grading. They literally have a 1.5 hour where they learn about teaching and learning and pedagogy, and they create workshops and worksheets, and they work in teams. But then they just come in and they're just there. They're just circulating, they're helping students, right? They're not grading or anything of that type, right? So it's a class. But it's just been better than I could have ever imagined. Okay, all right, so what we're going to do now is I'm going to launch into being the instructor, okay, for a class, and you get to be the students. We're going to run through a very abbreviated class period. It's going to start with a class launch. You're going to do a very abbreviated task, as we call it, just so you get a sense of what that is. And then I'll close the task. So we're not going to do this in the real way, but you'll get a sense of what's going on. Now, what I put on your table, on your chairs, is what the task would look like. Normally, I would just give this to the students and let them go with it. But you can read it later just so that you see what it looks like. And there is a periodic table on the back side. And as you're working, Erin, Sabriya, and my thought partner, colleague, Michelle Dusky, and I are going to be walking around, and we're going to be listening to what you're saying and supporting your learning, just so you get a sense of what we're doing. Okay, you ready? I'm turning into teacher mode now. All right, so what we've been talking about in the first unit of the class is matter, and we're trying to understand the properties of matter. And what we've been doing so far is we've been developing an understanding of an atomic view of matter, and specifically how those atoms are attracted to one another and how they move about. All right, we've talked about gases already and the kinetic theory of gases and how gases move, gas molecules move, and then we've also talked about how molecules of different shapes might attract one another or stick together. So we're looking at, in lecture 10 now, we're 10 lectures in, the lesson's called Attractive Molecules, and the question we want to try to answer is what aspects of molecular structure affect the strength of attractions between molecules. Okay, so this is a property of these molecules. Why are they attracted? Under what conditions? That's what we want to try to answer. Now, you're going to be looking at boiling point. Now, many of you are very familiar with boiling water. You know that you have water, you can put it on the stove, and it will sit there for quite a while. If you turn the stove on and the temperature starts to rise, you'll get to some point where you see this very vigorous boiling, and if you let it sit there, all of the water will evaporate. So what that means is all the molecules are floating around the room. They've escaped out away from the liquid. So the boiling point is the highest temperature at which a liquid exists. Not everything has the same boiling point or boiling temperature. So boiling point in the investigation that we're going to be doing is a measure of how strongly are these things attracted and how high of a temperature do I need to make these molecules fly apart. Okay, so that's what you're going to be looking at. Now, to support your learning, you're going to get a set of cards. I've taken some out so that the activity's not so long for you. We have a few extra ones that you won't see. But these cards have in the upper right-hand corner the boiling point. So you see 10 degrees, 78 degrees, minus 60 degrees. What's also on there is the molar mass. So it tells you something about the size of the molecule, the number of electrons. And then you're also going to see structures and names and chemical formulas. Now, we're not going to be using the bottom. That's for tomorrow, all right, when we talk about solubility. For now, we just want to look at this part of what's on there. So your job is to construct one claim, all right, about the relationship between the data that you see, the molecular structure and the boiling point, and make a claim about the pattern that you see, okay? You're constructing a rule for how these molecules are interacting. All right, now, what I want you to know is that as you do this investigation, there is a number of smart things that you can do. I'm going to leave this up because I'm going to want you to keep referring to this. Now, some of the smart things that you can do is look for trends in the boiling point. All right, does it get higher, does it get lower? Because it's a measure of how strongly those molecules are attracted to one another. Okay, now, you all learned way back when to control variables, right? But have you ever really done that? And so what you're going to find is that in order to make sense, you're going to have to think about keeping some things so that they stay the same while other things vary. If everything's varying, it's going to be really hard to draw a conclusion. There are multiple possibilities. There's not one answer here. You'll get to one, but the students in class get to quite a number of possibilities. I want you to make sure you justify your ideas in ways others can follow. So if you make a claim, make sure you can explain that claim. Don't be afraid to ask for people's reasoning. Don't be afraid to put yourself out there. Even if you're wrong, it's okay. It will help the conversation. And you can ask for people's reasoning and explore connections to the periodic table. Okay, so the reminder, the task is to construct one claim about the relationship between molecular structure and boiling point. Yes?
Teacher, I'm missing my cards.
I know, because if I had given you the cards already, you would be looking at them and not listening to me. So I'm gonna hand out the cards. It would be good for you to work, it's inconvenient, but work in groups of 3 or 4, whatever works, 2, 3, 4. But the most important thing that you need to do is make sure those resources are shared. So the first thing that I recommend that you do is just deal them out so that everybody's got a couple of cards so that then you can look together with them laying on your lap. It's not ideal. We have tables and whatnot, okay? All right, and we'll come around to answer questions and help. Oh, okay, we're going to get back together again. If you could put the cards back in the baggies, that would be really helpful if you haven't lost the baggie. Actually, my students in the class, just so you know, they're very good about kind of helping bring all the materials back together again, because we're very often using materials. Okay, yeah. Yeah, all right, so I heard a lot of really excellent conversations, lots of good ideas, starting with looking for trends in boiling point. I heard people not being afraid to ask a question like, what does the negative sign mean? Are the ones with negative boiling points, are they some kind of outlier? So I heard some really good questions about what the representations meant, etc. And then control variables when sorting. We tried to make visible the kinds of questions that we heard. We do this in the classroom. And for example, they're all C5H12. Same molar mass, but different structures. So in terms of controlling a variable, there was an interesting idea. And then as far as making a claim, shape seems to matter. It seems like if they're longer, they have a higher boiling point. And what does higher boiling point mean? Are they more attracted or less attracted? More attracted, all right? And then the ones that were more balled up had a lower boiling point. So shape matters. I saw lots of different possibilities. I hope you rearranged your cards in lots of different ways and saw different kinds of patterns. I heard good justification of ideas, and I heard people asking for other people's reasoning or just asking questions. And there was some connections to the periodic table. One student up in the front said, I have an S, I don't want it. I want a C. I wouldn't call out a student like that in class, but, but this student is okay with that. But I do often repeat something that I heard a certain group talking about, and I can look over, and I don't say it's that group over there, but they are so proud that I am talking about what they were talking about, or an interesting dynamic that was in that group. Okay? All right, and so just so you can see, we have these on the whiteboards around the room. We captured this one. The molar mass is the same, but you see that the structure is different, which might be what's altering the boiling point. This group has really low boiling points. What does that have to do with polarity? They're still wrestling with what that word means because they've just heard it. All right, and so now, just to close the class, remember we're talking about attractions and motions, molecules sticking together versus flying apart, and what you've just come to the conclusion is that their boiling point or the degree to which they're attracted depends on their polarity, unevenness of the charges, their shape, and then how big they are, numbers of electrons or molar mass. Right? Okay. Yes?
So you're covering the same class as the rest of the three sections. It would take a minute to make the statement, boiling point depends on polarity, shape, number of electrons, and move on, as opposed to taking half of a class period. Are you able to cover all of the same curriculum?
So I would say yes, because I can show you what the exam data looks like on very similar exams for the lecture sections that I did and these other sections. But what I'm asking them to do is something much richer. If I told them the rule, I think many of you in here who have very limited chemistry experience had a lot of questions about the representation. Somewhere up there's a question about what does it mean that the bond is longer, or there's all kinds of things that come up that go unanswered. And so that simple statement that you make, the student then goes home or back to their residence hall, they may or may not have a study partner, and then they have no idea what's going on. And I'm asking not for them to repeat this back. I'm going to give them another problem where I show them molecules, which you'll see when you look at the exams, and I'm going to ask them to draw on this experience and actually come up with draw a conclusion or an explanation of the trends that they see. So a lot of it is just cutting out a lot of the details that we all want to put in there and get to the core of what we're talking about. So.
They do also watch a video lecture after.
Oh yeah, sorry, they watch a video lecture after class, which they're totally prepared for. Sabriya is going to get to, because they've had a chance. What I found when they're sitting in my lectures, I'm over most of their heads. They don't know what's going on. They have to go home and then struggle with it. This way, they get all their questions answered. Then they go home and they watch 20 to 40 minutes, it varies, video voiceover on PowerPoint, and that's where I kind of refer to this, I bring it together, I give more examples, and we get a richer understanding. Okay.
Okay, so before we launched you all into the task, Erin introduced you all to our organizing principles, and so I'm going to take a few minutes just to talk you through how these organizing principles help to shape the design of the task and what happened in class. And the first one, and not necessarily the most important, but it's a great place to start, is really thinking about what we want students to learn, right? Because we want students to have this sort of rich and connected understanding of chemistry, we needed to decide what the starting point, or what sort of like the first node of that connected understanding would be. And in our most recent iteration, what we came to was thinking about attractions and motions, right? And so what you heard Angy do during the task launch and close was make connections to what students would be doing in the task launch and what they had done in the task close back to these larger ideas. And we took these ideas and connected them throughout all 4 units of the course. So in the first unit, which is about matter, we're talking about atomic views of attractions and motions. In Unit 2, which is about energy, we're talking about changes in attractions and motions. Unit 3 is about equilibrium, so sort of the competition between attractions and motions. And Unit 4 is about measurement, so modifying attractions and motions with light. And there's also some refinement of some earlier models introduced in the course. So starting from these central ideas, we started to build the lessons and considering what concepts we wanted students to be engaged with, and really started thinking about task design. So task design was also a way that we were able to engage and support students in collective chemical investigation. And in thinking about what we wanted students to do, right, because we want students engaged in chemical practice, we needed to start with data, right, because that is how science operates, right? You're creating some data, you're analyzing some data, you're reporting on some data. So we needed to give them data. We also wanted to be sure that we weren't introducing new chemical jargon. And this was in large part because we want students wrestling with ideas and concepts, right? So as Angy mentioned, many of you may not have taken a chemistry class in some time, right? But we heard you all doing some really rich and wonderful chemical thinking, and you were able to do that without knowing what polarity is or memorizing what the trends are in periodic table, right? So we wanted students to be able to do that without also having to keep track of language, right? So you're not learning concept and language at the same time. Also, because our students are coming from a wide variety of chemical backgrounds, some of them may have taken chemistry as seniors in high school, some of them may have taken it as freshmen in high school, right? And so, memory is fairly short. We wanted to be sure that we weren't privileging students who either had potentially more chemistry background or more recent chemistry preparation. Also, we wanted to be sure that the product of the task allowed for multiple valid approaches and that those approaches required multiple types of skills and practices, right? That way to help support some interdependence of the team, right? So because we want to value all of the brains at the table. In addition to creating the task in ways that allowed for these multiple approaches, we also wanted to be sure that the data was complex enough to allow multiple ways of engagement with it, right? So you all worked with some data cards that we've created. We had other types of data cards. We also had students work with data tables, also online animations and simulations, and different types of images and drawings. Another way that we tried to support team interdependence was a rotating role called the team leader. And the team leader's responsibility was, one, to read the brief description of the task, but also they were responsible for communicating group thinking. So here is just a representation of an instructor coming up to a table and asking what's the team question, right? Because what we wanted to try to avoid was having one-on-one interactions with one member of the team and an instructor, right? And here the team leader is saying, how do we know if something is dissociated or just dissolved? Now you could imagine that if the instructor is coming and asking what the team question is, and the team leader's like, oh, I don't know, right? Because that happens. The idea is that we would then have the instructor walk away, just suggest, okay, well, check in with your team, I'll come back, right? Because we really want them to be able to think together, so they're able to value themselves as rich thinkers. And finally, reframing scientific brilliance. So during the task launch, a huge part of that is just trying to provide some explicit language about what it means to be scientifically brilliant. So providing these more expansive definition of scientific brilliance, and a definition that is centered on practice, right? That is not about those larger societal narratives that Erin spoke about in the beginning, right? It's creating more space so that students can see themselves within the landscape of scientific brilliance. and doing that through the Smart Things list. And then during the close, we're taking what students have actually been saying and doing and thinking in their questions and connecting those back to authentic scientific practice, right? Because very often students are very scared to ask questions because they feel like, I'm not going to be seen as smart, or this is a stupid question, or it's X, Y, or Z. But by really valuing this question asking process and the ways that students are thinking, we're supporting them to see themselves as brilliant. Or ideally, that's what we want to be doing. And this is actually a quote from a closing where Angie closed the class and told the students, you guys are asking great questions and that are getting me to think in different ways. So can you imagine being a first semester freshman in this class that is supposed to be really hard, and your instructor, who is an established chemist, is telling you that the ways that you're thinking and learning is really getting them to think in a new way, right? How powerful that might be. So before we transition to talking about what happened outside of class, are there any questions about some of the in-class design things?
I'm curious, you captured a lot of questions and reflected them back to the room, but do you actually also answer them? Like people, all the questions you hear, say when you're walking around the room, like what does those different fonts mean, like all those ones you mentioned, would you actually, as part of your class, answer those?
No, so usually they're a part of the conversation. So similar to the ways that we were trying to eavesdrop on you and being unreasonably close to do so, right? We didn't want to necessarily disrupt conversation because, again, right, we're trying to create this environment of interdependence within the teams. If students, if there is a question that they have that they can't amongst themselves ask, then they would raise their hand to ask a teacher scholar or a GSI or one of us. But yeah, we usually didn't disrupt sort of that investigative process.
So I just wanted to suggest that you might want to reconsider rewording the smart list thing, the smart list title, because I think that in some way using the word smart feeds in precisely into the type of framing that you're trying to dismantle. It sort of sets up this dichotomy, whether if you do it, you're smart, if you don't, you're not. You might want to think about maybe terms like useful practices or productive, I don't know, some other term, but it strikes me that very term feeds into the ways of thinking about brilliance and success that you're trying to do away with.
Interesting.
Did you come up with game rules for the group, or do they make them themselves, or just sort of norms to establish communicating with each other, or lay any of that out?
So at the beginning of the semester, we tried to have students sign a contract about how they would engage with each other and making sure that they showed up to class, et cetera, et cetera. And beyond sort of the role for the team leader, I think we didn't have too many rules about engagement.
A lot of the norms are getting built through what's coming up in this original launch of this list that we're providing. So one of the things that we built in is the idea of using the middle space, that everyone needed access in terms of language practices. Some of the norms were using language that makes sense to other people as opposed to just trying to use language that makes sense to you. When you watch video, you can see that the practice that students is engaged in is collective. It's not a bunch of individual people, and so I think I'm still trying to understand how did we build that, because in some ways this thing happened, and now we're trying to learn how.
We also, the first set of groups we constructed, we tried to get the introverts together so that an extrovert didn't kind of take over the conversation. And then we purposefully walked around to make sure that nobody was leaning back and that the materials were centered so that everybody was participating.
Yeah. So I guess here, and there.
Yeah, I'm coming from the perspective of majors on campus that aren't impacted. So going back to your theme of the perception that these are weeder courses. So if we create conditions where more people are succeeding, how does it function that the major itself continues to, I'm assuming, not just keep growing in its capacity to accept students that are thriving? Where where is that rub in terms of,
So I'll take that, because we're actually not weeding students out in Chem 1A based on grades. They are choosing that they feel weeded out, right? And so I would argue that what we're trying to do is not make them feel like they're the weeds.
Yeah.
Right? No student should feel that way.
And I think also a part of it, like the impetus for us, is really trying to create a space where students feel like they have a choice, right? Because like having choices is a lot better than feeling like you're being pushed out, which is what's happening, right? So if I have a choice about whether or not I want to continue in science, right? Because people just change majors just because they're changing majors, right? That happens in non-STEM majors all the time. So if students are now not feeling like someone is making the choice for me that I shouldn't be here, right? Or that the system is, however that gets framed for them. I think, I mean, in terms of thinking about ballooning out, right? I guess that's what you're saying, right? That the majors are just, if there's too many people in the major, I'm not sure if that'll happen or not, but I think we should think about systems in which if more people are successful, it's going to be a problem, right? I guess. Yeah. There was two more questions.
I just wanted to ask quickly, so the undergraduates, they take a course, but I was just curious about the GSIs. Like, are those consistent over semesters? Do you train the GSIs? How does that work?
We happen to have the person who trains the chemistry GSIs here.
All GSIs on campus are required to take a pedagogy course.
Yes.
Yes, and so all of Angy's GSIs are part of mine.
And I purposefully select GSIs who have an interest in this kind of learning, who've had experiences with it, and they've been wonderful.
And then we plan a one-day, it's like an 8-hour-long orientation where we try to support our GSIs and teacher scholars to understand the vision, and we do tasks, and we talk about how to support interactions. And, yeah.
Oh, hold on. There's one more question back here.
I have two questions. The first one is, how often do you rotate the groups?
So for the semester that we're talking about, I think we rotated twice.
Yeah, but I landed on 3. And what's wonderful about it is I actually tell the students, they miss their old group sometimes, but what I tell them is they can take on a new personality. So if they were the quiet one, now they can maybe be the one who is speaking up more. And you can feel the energy in the room go way back up because they get into this rut of who they are in the group. So changing it up is helpful. And I assign them, and I pay attention as we go along to certain students who I want to make sure are in the group that supports them.
And my second question was, it's more on the recruiting side because you mentioned the program. I guess what kind of language is used sometimes to try to recruit a student just so that they're not interpreting it as like from the beginning, like, oh, why am I being reached out to? What does this mean?
Yeah, that was definitely hard in the beginning. Like I remember fall 15 trying to figure out what that language would be was difficult, and we ran into some hurdles. I think once students found out that it was a good thing, it was a little bit easier. Yeah, at some point it was like accelerated learning. Now. But we talk about it being a collaborative learning space, that it's smaller, that it's group-centric. And I think also because there's so much lore with students on campus at this point that it's easier sell than it was in the beginning.
I'm turning students away who've had lots of AP classes and clearly will do fine in a larger class because I really want to attract the students who will benefit the most, right?
Yeah. Okay, so we should move on so we can get to all of the things. So the next section is just going to be about sort of the things that we design outside of the classroom, right? We're trying to do all this explicit work to reframe Brilliance and science in class. We need to be sure that what's happening with all of the things outside of class aren't working against all of that work. And so we're coming back to these principles. And the only difference here is instead of engaging students in collective investigation, we're just, still trying to engage them in investigation, just not together, because we don't give group exams. So the first thing, which we mentioned a little bit earlier, was a video lecture. So after class, students are provided with a pre-recorded video lecture with voiceover on B courses. And the goals of the video lecture are to sort of review the task and like the major ideas of the task, to introduce formal language, because it is important for students to know scientific formal language. But now that they've had opportunities to sort of wrestle with these ideas, we can just slap a label on it, more or less. And also to introduce some of the concepts that we weren't able to during the task. We also, again, because we're trying to support students to have this connected understanding of chemistry, we call out the ways that the concepts that we're covering in a given lesson are connected back to other concepts within a unit or concepts that we've talked about in the course overall. And then finally, because we want students to see chemistry as relevant to their everyday lives, we provide a number of different examples of how these concepts show up in every day. So if we're talking about pH, we might talk about soil acidity and how that might affect like the color of a flower, right? So next, we really had to think about quiz and exam questions because so much of students' grades come from quiz and exams, and the design of exams really communicate what you as an instructor or a designer value, right? And because we're trying to value practice and center practice, we needed to be sure that our questions reflected that. We wanted to be sure that we were engaging students in chemical practice as a part of these quizzes and exams. So quizzes and exams were these interrelated sets of questions that were centered on data, right? Because we also want to be engaging students in the types of practices that we had them engaging in during the task. So here's an example. It's just a table with thinking about intermolecular forces. And then we have multiple choice questions, and we also have free response and some where students are asked to draw things. But in order to do these things, they really have to be sort of like analyzing and interacting with the data in the same ways that you all did with the cards. So in addition to homework, quizzes, and exams, we also wanted to create a non-exam assessment, right? Because exams are such high stakes things. So we wanted to create this extra assessment that also centered communication as a valuable scientific practice and provided students with the opportunity to develop some fluency and some flexibility with their science communication. So we came up with the Communicating Science Project. So for this, at the beginning of the semester, students chose either a hormone or a toxic metal salt that they worked with throughout the semester, and they were required to teach their audiences about the chemistry of their substance. And there was also an opportunity for students to do peer review, which for some of them was fairly powerful because they got to see how other people made sense of things. So this is an example of one of the prompts. This was in our Unit 4, where students were asked to teach their audiences about spectroscopy and how they could learn more about their given compound using spectroscopy. So this is an example. So they had two audiences. So the first audience was the other students and people in the classroom. And so for this group of people, students were asked to use formal chemical language. The other was their friends and family. And for this, students were encouraged to use informal language. We required them to define any and all scientific words. And we also encouraged them to make references to either their own cultural background, pop culture. Here, this is Joey from Friends, if you were familiar with him. But the idea is really just to like teach your audiences about chemistry.
All right. So we're inviting students kind of into participating in new ways, but it could still be very possible that they're doing new kinds of participation, but not necessarily reflecting on some of these unexamined assumptions that they have about science. And so we, 4 times in the semester, once at the end of each unit, gave them this thing that we call the science skill reflection. And we use this as an opportunity to continue to define kind of what is necessary for doing science. So we picked these 5 skills, things like persistence, bouncing back from setbacks, diligence, skepticism, and students would pick one of these, and then we'd have a series of prompts that would help us kind of define what that skill meant. So, for example, when I struggle, I remind myself that encountering setbacks is a normal part of the work of scientists. So they could kind of see where they were at in relationship to that skill. And then we asked them, okay, well, describe a moment when you were actually encountering some kind of setback. How did you respond? Just to get them to be reflective about their participation. And what this allowed us to do is then read all of the things that students were saying and give them some class feedback. And our purpose there was to kind of publicize and normalize some of the things that they were experiencing and also remind them that this is some of the most intellectually challenging work that they've taken on, and that the things that they're feeling are actually just a normal part of doing science. So we'd say things like, many of you said you're feeling nervous about holding others back with your questions. But actually wrestling with ideas, not yet knowing how to construct an explanation, this is important to the work of doing science. And we'd often say, these are things that we as professors and graduate students experience. So just trying to set the tone that this is normal and important. And then it also gave us a chance to point students to resources. Okay, so we wanted to just take a few moments to share with you what we think this class is making possible for students. So through an analysis of video, we are seeing students engaged in scientific practice to actually build accurate and new chemical understandings. When we probe their sense-making about what it means to learn chemistry, good at chemistry, we're finding that their answers are anchored in practice and therefore kind of more inclusive. And we're seeing positive shifts in how students are viewing their relationship to science. So I'm going to walk you through some of this data. I want to show you an excerpt of video to give you a sense of what this class feels like when students are working together. And I'll tell you, I want to say enough about it so that the video makes sense to you. And there's also transcript that was put at your seat so you can kind of follow along. So this video comes from the end of the beginning of unit 3, which is the equilibrium unit. Students are just getting introduced to acids and bases. The day prior to this video was the first day of the unit where they saw molecular views of strong acids and weak acids and, looked at extent of dissociation. Yeah.
What part of the semester is that?
It's like basically halfway through. Yeah, it's day 24 of class. And in this task that students are working on, they've been asked to construct a model that accounts for the composition of the reaction mixture, now looking at when acids and bases react. So this is the first time they thought about these reactions. And they've gotten a series of acid-base reaction cards that look something like this, depicting a strong acid and a strong base, the molecular views of those. And in the cards, the NaOH, that's the base, varies in terms of its amount and in terms of its volume. And then students can see what shows up in the reaction mixture. They've been asked to examine the similarities and differences that they see in the solutions. And then one prompt asks them, okay, well, think about sometimes those red dots, the H+, shows up in the final reaction mixture, and sometimes you don't see it. So why is that happening? And to give you a sense of the thinking that comes before the video, this student in the back, Cadence, has suggested that the reason that they see H+ or don't see H+ in the end depends on the amount of base that's reacting with the acid. So she's made this claim and used evidence, those two cards, to support that claim. And then Keisha, the student at the left, has kind of added a causal explanation to that. So she's suggesting that maybe what's happening is that the H+ is getting dissolved and then it's disappearing. And so they kind of try to make sense of this, and those two students, Keisha and Cadence, say, okay, I think we've come to a conclusion, and they start to write. But Olivia, the student on the right, is not quite satisfied with that. Disappearing, in chemistry we're trying to make sense of behavior and interactions. What does it mean that something just disappears? And so she says, I don't really know where they go, where the H+ is going. So you're going to see Keisha, she stops writing, and she's about to try to help Olivia make sense of this dissolving explanation. And you're going to see them kind of negotiate together and come to this new explanation that's more accurate. It's about the H+ and the OH combining to form water. So as you watch, I just want you to think about the practices that the students are engaged in and what's maybe striking you about what you're seeing.
Because there's enough things to dissolve these, but since there's more of these, not all of them can be dissolved either.
Sorry, can you say that again?
Like, because there's more of this, it can dissolve all of this, so we don't see it anymore. But since there's more of these, not all of this can dissolve it, so there's going to be some of these left over. Does that make sense?
Yeah, but I'm just like, I'm still wondering like where they all are. Like if you have HCl minus and then Na plus, OH minus, you have 2 millimoles of NaOH. So you have this. this together. And then you have 10 of NaCl. So this one and this one, what happened to the hydrogen?
So that's the
Like, where are they? Or like, where did they combine? Did this combine with the OH? Is that the water? That might be the water. Like H plus, OH minus.
So you could say it's the water.
Yeah, that might be the H2O. And that would still make sense to like
that's like
water. Yeah, the background. And there's just some hydrogen left over that can't bond.
Oh, sorry. Well, I guess we can't rewatch it. In the end, they say that can't bond, and then Olivia goes, genius, and then they stop. So take a moment to think about what practices did you see and maybe what struck you or stood out to you about what they were doing together. I'll give you 2 minutes to chat with each other. All right, we're going to come back together in 5, 4, 3, 2, 1. All right, thank you. Does anyone want to share out what they noticed or saw that struck them? Or any practices that they saw that they thought were interesting? Yeah.
So one of the things that I observed is it's in the high schools, this is how they're now being taught. So this is how the Common Core curriculum is taught. And which means that the students who are coming here, who are coming out of high school in the United States, are very accustomed to this method of learning and of having group conversations and of teaching each other. And I wonder, and maybe your selection method is focused entirely on domestic students, but in my department where there's a lot of international students, having that sort of a group approach, we encounter more problems. The students not being willing to engage. So what stood out to me was they're all quite willing to engage, and it reminded me very much of my son's high school question.
Interesting. Yeah. It seems like you'd have to do a lot of thinking about what students would need to hear to support them to be successful in those teams if you have students from different kind of outside of the United States. Yeah, good point. Yeah.
Well, I was just going to comment too that you mentioned that this was mid-semester, and so I'm imagining in the first class or in the first couple of classes, the group dynamic wasn't the same, and that this was fostered in trust over a period of time where they felt safe to explore and to acknowledge not knowing and those types of things.
Yeah, she was just suggesting that in the beginning, the group dynamics don't look quite the same, right? It takes them time to kind of build the culture where this kind of thing, where asking questions is okay. This is the first day that this team has worked in a group together, which is kind of interesting. So I think it's maybe suggests to us that the culture that's getting built across the class is traveling across groups. Yeah, one last thing that someone noticed.
I just noticed how much they seem to care about each other. There's so many different ways people can express confusion or say, no, that's wrong, or that doesn't make sense, and be very confrontational about it. And instead it was much more inviting to, hey, let's explore this a little more together in a way that I'm not sure what you all did or if the students brought that and you made the space for it, but it was really unique.
Yeah, that sense of care was talked a lot about in interviews. Students connected the care to their own learning, and how one student talked about like love. They felt like this was a really loving space where they could just bring themselves to it. And I think that does matter for the ways that students are willing to engage.
Yeah, one student who was particularly struggling with lots of personal issues, by the end was saying he felt this was a safe space. Which I think was really important, that you could come in and feel like you could be yourself.
Right. Which really matters for learning, right? It really matters for the kinds of things that you're willing to do, the kind of intellectual risks you're willing to take. Yeah. So I won't say a lot about this, but we collected video across teams and across tasks over the semester. And so I analyzed across 10 tasks, basically the participation of one team in each task, and looked at the different practices. And there's a lot of practices that they're engaged in, but in terms of getting interrelator reliability, I ended up looking for these 6. So asking chemical questions, not just clarifying questions, but questions that were chemical in nature, identifying relationships or patterns in data, justifying ideas with evidence or some kind of reasoning, challenging claims in the same way, and then constructing causal explanations. And a lot of these practices, when I coded for them, they're actually happening across students because one idea is getting suggested, the reasoning is getting backed up, and so these really are effective practices. And then in course reflections, at the end of the semester, we ask students, all right, just take a moment to reflect. How have your ideas about chemistry learning either been changed, challenged, or confirmed? And so there were 86 course reflections, and not everyone who answered that prompt said what they used to think, but of the 57 students who did describe what they used to think chemistry learning was about, 81% actually referenced memorizing facts or executing procedures, like they thought chemistry was about doing math. So to give you a sense of what that sounded like, in high school, honors chemistry focused mostly on memorizing chemical formulas and periodic tables. Tests were based on regurgitating info from a textbook. I was forced to memorize so much, and I didn't feel like I was really understanding. So students talked a lot about actually not realizing that chemistry was something that you could make sense of, that it was understandable, that they ended up doing a lot of memorizing in their classes. And then of the 75 students who did answer the prompt, 100% of them talked about learning chemistry as building new understanding. And so they were talking about what that understanding meant or how you got to it. So in this class, we studied trends ourselves. We learned ways in which we could apply logic and explain trends and overall question the reasoning behind the chemistry. For example, rather than just learning about ionization energy, we observed the trends, we tried to understand them, and even tried to create shell models. So they were naming the practices of chemistry as they talked about what it meant to learn. They kind of got that they're learning as a chemist learns. And then in interviews, I interviewed 21 students, Sabriya and I did, together, and we asked students chemistry. And a couple things stood out to us. The first was that students' responses, in them, they were kind of rejecting some of these dominant cultural understandings. They started by telling us, well, what it doesn't mean or what I used to think is, and those were things like knowing information, getting correct answers, using big words, or referencing some kind of natural ability or good grades. So this student, Kalani, says, well, before this class, I thought a chemist was someone who was smart, got good grades, someone who knew chemistry, and if they explained it to a person with no scientific background, it should just sound like gibberish. Which, yeah, a lot. So the fact that without prompting, students are telling us what it no longer is to be good, tells us that they're aware of the narratives and they have to contend with them. And what students did end up saying is that understanding, it's about being able to explain not just to someone else or not just to myself, but in ways that make sense. They talked about chemistry as if it was a human activity. They talked about, practices for analyzing data, orientation toward inquiry. Those are things like being inquisitive, being skeptical, being open-minded, things like that nature. And then there were 2 students that really held on to, this is about good grades because society thinks that it's about good grades. So they had kind of this more critical systems view of that. So Kalani says, now after this class, I feel like a good chemist is someone who can make the connections, someone who understands chemistry, who can relate it to people, because you can't just tell someone there's global warming, but if you're able to connect it to their understanding, then that's a good chemist. So really making it feel relatable. Yeah?
If you were to poll the faculty of chemistry, would they say a good chemist is this quote, or would they say a good chemist was the previous quote? Because the question is really, once they get out of Chem 1A, they have to go on and take chemistry from other people in the department. Mm-hmm. And you can't control your colleagues. Mm-hmm.
Yeah.
So what happens after this?
Yeah, well, in fact, I was a GSI for the organic chemistry class that comes after this with this particular student, Kalani, and that professor put up a grade distribution and circled the lowest distribution, which she, I think, was in, and told the class that if you're in that lower section, there's a natural ability problem. I think he used the word innate ability. So, yeah, so that's interesting. I'm obviously these are things, as I think about this and as I write about this, my sense is that students, I think, are developing some kind of epistemological toolkit that they can take with them, that they're still going to be in these spaces where they're going to experience all these narrow messaging, but they have an experience now of competence, right? Where all of them kind of know that they can figure this stuff out. They have a great sense that they're learning a lot, and they take that with them. And so I see a lot of increased persistence, I think, and they have a counter narrative to kind of draw on. But yeah.
And so that's the real test here is we have a lot of wonderful support structures external to the class. So for the first class that they encounter, can be constructed in a way that launches them and makes them resilient against the other types of experiences. They also go in with a friend in this class, so they have a close connection to someone they connect with. You know, have you followed the data that we're trying to
Hey, Andrew.
My students now were in this class, and it was really cute in office hours. I was suggesting how do you study for the test. I was like, it's important to get in groups and try to teach each other. And one of Angy's former students, like the students were just like, oh, I don't know how to find a group. And one of Angy's former students goes like, my friend and I are in a group. You can come be in a group. And she just passed her phone around the room. Everybody entered their emails. And I was like, yeah. All the group leader has to have is a plan, and she's got the plan. So, and it was just so sweet to see this student just reach out and help these other people that normally were isolated.
Yeah.
Well, and we encourage that sharing of phone numbers and study groups.
They create Facebook groups. They have in at least the past 2 or 3 years, Facebook groups to get together and study in mass. Because I think fall 15, they were 40 of them trying to find space on campus to study together. And I was just like, that might be too big for a study group, But I was just glad that they were doing it, so I wasn't going to judge. Start the behavior, refine it later. So one thing that came up as a part of the interviews when we were asking students what it means to be good at chemistry was this really awesome follow-up question, right? You've defined what it means to be good at chemistry. Based on your definition, are you, right? And it was, as someone who designed the course and watched these students power through, many students ended up with this connection oh, I am good at chemistry, which is awesome to see a number of Black and brown students make this realization for themselves. But in addition to this interview data, we also did some survey work so we could get both information about students in our class, more students in our class than we would ever be able to interview between the two of us. And also from the traditional course, but we're not talking about that today. So we gave students a survey in September at the beginning of the semester and in December just before the final. And one of the questions or one of the items that we asked them were I am good at chemistry. So this is looking at 66 students who responded to both the beginning and end. So just to orient you, 1 was strongly disagree and 4 was strongly agree. So they're starting off fairly low, closer to disagree. And we do see this upward shift. Still not, 4 for everybody, but within a semester and also within the context of everything else that is going on in these students' lives, it felt important that, more students are saying that they, are feeling a little bit better about being good at chemistry. Also, because we want to support students to see themselves and science and the relationship to science a little differently. We see a small shift here in response to being a scientist is an important part of who I am. And then finally, in September, the item was when I'm in a science setting, I feel a connection to the science community. And students are a little bit closer to agree than that. But we see this pretty large and statistically significant shift upwards by December, where they're really feeling when I'm in Chem 1A, I feel this connection to the science community. And that's really something that is important for us in terms of trying to build this community of learning. So I'll pass it off to Andrew. Oh, sorry, there's questions.
I wonder whether it'd be worthwhile to do that with the people that are taking Chem 1A that are in this course.
So, yeah, we have that. We're just not showing it for the sake of...
You do.
Yeah.
You might expect actually the opposite opposite trend.
So I
That
can,
would look much stronger.
I can briefly walk you through this. Okay, so for I Am Good at chemistry, the students in the redesign course, they start off lower than both a match set. So I did some matching based on high school chemistry, if they were repeating, and if they were underrepresented minority. So they start off lower than a match set and a set with the same demographics as a larger set. This endpoint is the same for everybody. And the students in traditional course, there's no shift for them. Being a scientist is an important part of who I am. If I remember correctly, the students in the match set, I think this goes down a bit. For this one, our students start off lower than both a match set and the traditional set, and but they end up significantly higher, both because of this increase, but also because the students in the traditional course that actually their mean response decreases by the end of the semester. So yeah, so we had it, but there was.
I had the same question.
Okay.
Mm-hmm. So I feel like we're at the beginning of this kind of conversation. This is a hard class. There's no question, there was no watering down. You're watching students go through this, trauma because they're used to getting A+ and everything was easy, and then suddenly they don't get such a good grade, and trying to help them persist through that and come back out at the other end feeling really good about who they are and what they're capable of. And many of them tell me that they're just really happy with what they've been able to accomplish. And I really set the bar as where did you start and where did you end up, as opposed to what grade you got. I really try to leave the grades aside and get them to be proud. And they'll tell me they're proud that their exam grade went up, or that they understood something and could explain it to other people. Now, there's a lot of challenges. We already had a question about coverage. So choosing concepts for a 40-minute task that are rich, that get a rich understanding, that really build towards what I'm going to say in the lecture is hard. Finding relevant and accessible data. Michelle Dusky and I have many years of experience of trying to understand some biological data set to try to simplify it so that we can use it for the students to make sense of. Keeping tasks open while providing sufficient support. All right, that balance is tricky. We were too closed in the first one. We were too open in the second one. We've come back. Supporting equitable engagement is not always easy. Sometimes it's the end of the semester when I talk to the students who should have reached out earlier. I can help them from there, but I wish I could get to all of them sooner in terms of their engagement, because they just feel that they're holding other people back. They feel like they're not smart enough and all of that. And then convincing the students that they're capable. That's not so easy, right? We've been at this for a while. Just so you know, I taught the lecture sections through 2007 to 2012. I did it collaboratively with other faculty in the chemistry department. So the whole chemistry department, forget it. They don't all agree on exactly what emphasis and focus and whatnot. But at least I can say that there are at least 5 other faculty who've agreed that this is the content that we should be covering. We did a lot of restructuring then into units and tried to emphasize the central ideas. Then in 2013, Erin and I worked with some of the students who were really not performing well in the lecture section so that we could start to understand why they were struggling, what was going on. And then we started this redesign in 2015. We started with worksheets that we then redesigned to the tasks that we showed you. And then we've continued to do refinements and really think about how best to support the students. One of the things that I think worked pretty well is we created a reader for them. So we give them a template for taking notes in class, but I also gave them a copy of all the slides with a lot of information missing. And I could see that these students were listening to those lectures and taking notes on there, because I could see this book was filled with handwritten notes. Okay? All right, and so I think from there, we just want to say that it's important to create a strategic plan for the redesign. you want to learn the landscape, you need to find partners, you need to work in the literature, look in the literature, and talk to students. I think when you heard what they were saying in the video, you could see these are talented students. That group did pretty well in the class, but you can see how they're struggling with the language. They're just learning it. And they're often not using scientific words at the outset, but they'll learn them. So you want to learn about the students. You want to make small, deliberate, and tenable changes. I don't want to pretend like we did this overnight. And then you want to create avenues for student feedback about the course innovation. So we had a really strong relationship with these students. I stay in touch with them. They tell me things. I admit when I make mistakes. That makes them more comfortable to talk about what the issues are. So I think what we want to do now, just for a remaining time, is really talk about what's something that you can do to disrupt systems of equity in your classroom. Now, I realize not all of you have a classroom, but I think if you could get together with another person or with a small group, why don't you think about what are some of the things that you think might translate into classrooms that you've been in or classrooms that you're teaching? Okay, so let's just take a couple minutes to do that, and then we'll take questions and close. 5, 4, 3, 2, 1. Okay. We would just be curious to hear just a few things of what you think are transferable. It would just be helpful to us. Is there anything particular that you discussed? Go ahead.
So I run a program for middle school girls, but we have high schoolers and volunteers who talk a lot about their experience. I'd be really interested in having like our high schoolers talk about science skills, the way they see their science skills and how they've developed them, and be able to talk to the middle schoolers about like, I'm a good scientist because I can do these things, and kind of already get that framework in for the upper girls.
Anyone else? Oh.
I can say one question. I didn't say it in the group, but I teach a class called Redesign, where diverse teams get together and extract biological principles to make new inventions doing this. And so we have 40 design teams, and the inequity issue is enormous in terms of getting everybody to participate like you did in your class. One thing that's helped is to work with the Haas Business School in Sarah Beckman. They actually have a module in courses that's available to everybody. You're saying yes about that?
Yeah, so I work with Sarah Beckman.
Yeah.
We teach teaming tools.
Yeah.
It's all on a website. If anybody has questions, feel free to
Please look at this, because I think you can adopt it like this. And one of the things that's been very effective is this notion of early groups doing this thing called the collaborative plan, where they talk about what each has with respect to the value of their unique voice and how they can piece this together to have everybody make a contribution that's beyond what any single division. So talk to these guys. It's a great resource.
Thanks. So I'm going to just thank some people, and then I'll open it up for any remaining questions that might be there. So I need the next slide.
Oh, sorry.
I think the main point that I want to make is that trying to do something new like this on the campus really requires a lot of support from people. And I have to say, personally, that the staff who support what we teach and the students have been absolutely phenomenal, so helpful. And I could not have pulled this off without multiple staff figuring out a classroom space, figuring out how to schedule this, figuring out how to get the students here. So I just want to really acknowledge that. And so you can see there's been quite a number of different people who really made a difference on the staff side. There are some great colleagues in the chemistry department who are supportive of this. And the researchers that we've had, undergraduate researchers, GSIs, undergraduate teacher scholars, and I'm just saying how lucky can I be to have these two on my team. And so I don't want to make it sound easy, but I want to say that this is a campus that's entrepreneurial. So if you reach out, you'd be surprised at it's challenging, but you'd be surprised at the number of people that will come and help you, right? All right, so with that, go ahead.
Thank you. So I'm on the National Family Sciences Board of Life Sciences panel. They had a whole session on introductory courses and explain both not only chemistry but in biology and physics. But if you had to pick the one thing that would most affect STEM engagement, retention, and success, it would be what these guys are doing. And so I just think this is spectacular and great challenge, and you've made so much progress, and I think we need to thank you. So.
Any remaining questions, or yeah?
How does the final grade distribution in your class look like in comparison to the other sections?
So comparing my sections that I've taught before, let's just be honest here. We write an exam, and sometimes we have a question that's a little crazy or a little too easy, right? Okay, I'm just to be honest, but this is what it looks like. These two, the green and the blue, are scores on exams from F11, 2011, 2012, when I was collaboratively teaching the large lecture sections. So my other colleagues agreed on the level of these exams. And then I've written very similar ones since then, and that's the gold and the red, and those are for the redesigned classes. And what you see is that they're pretty similar, right? I mean, once in a while I'm a little too easy, and once in a while I'm a little too hard, but.
I mean, in my experience, like when I started practice-based flipping the class, except all that, like the grades were just started going up to the extent where then, like after a few years, I had to answer to the chair because I had situations.
Oh, I see. So honestly, one issue here also is that these two sections have a large number of students who've had 2 to 3 years of chemistry. So they're very privileged students. And so our goal was to take students who come in without all of that and really bring them right up, right? Okay, question?
I was really struck with your science communication project, but with 100 students, how do you guys go about giving feedback on those presentations?
Yeah, so in the iteration that we're talking about here, it was students submitted this to B courses, and because there were extra bodies to grade outside of the GSIs, we graded them and provided feedback via B courses. In this last iteration in fall 17, because we needed to move forward with writing a thesis and trying to learn how to and analyze some data, those extra hands weren't available. So what Angy and I sort of came to was merging the project into a part of the exam, right? Because the exams have to get graded no matter what. We still had space for a peer review, but there was less feedback there wasn't as much detailed feedback from us in terms of that first grading, but they did get some from the exam. So just trying to utilize technology to make things more tenable while still trying to give students opportunities to develop these skills.
They liked the project. They liked doing this because it was fun to look up some, property of some compound.
Yeah, and I think a lot of them had fun just thinking about how to talk about chemistry, and also as a person who was reading them, you really got to see the really rich ways that they had come to understand chemistry, outside of having to sort of be taking a sort of stressful exam where it was just there are clearly connections being made. You can also see some of the misconceptions because we still have to figure out how we get students to think about equilibrium properly. But yeah.
Go ahead.
On more of the campus level, is there a vision that all courses would become like this course, or all introductory courses would have a section, or what's the vision?
So my goal here is to at least have this class maybe even double in size, offer 2 sections, and stay put, all right? Because these students really need this bridge. So that would be my first goal. But I would argue that a lot of the intro courses could really benefit. It would be great for everybody, but if we could at least do it for the students who we know are underserved, I think that would be great. And it's not, yeah.
So can I ask a follow-up question?
Sure.
So if we're not reforming every course, then what can we do in the more traditional courses to be better and more equitable?
That's a good question.
That's an excellent question.
What?
I don't know, just some conjecture. I guess one thing is trying to be more mindful about what you say to students, right? The example that Erin mentioned earlier about like the teacher talking about like, you know, this is sort of an ability issue, right? Like that's something you probably should, like if you're trying to support equity in your classroom, creating the like, or like playing on those lines feels inequitable or is inequitable.
We also emphasized almost exclusively the positives, right? If you listen to us, we tend to say you got that wrong, as opposed to, I can see where you were thinking and you're well on your way. Let me give you the next step, right? I mean, just really flipping the way that we talk to students and making assumptions. We make assumptions about students. And my experience is it's incredible talent, especially from these students who've come here basically first generation. They filled out the application, they figured out the financial aid, their families don't entirely understand what they're doing. They're amazingly talented and resourceful, and they just need a little bit of extra support, I'd say, in navigating this academic space that other students know about, right? Anyway, I'm sorry, did you have something else?
I guess the only other thing was just to think about how you talk about science, right? Because there are ways, like, you know, you might not be able to do a card sort in a classroom of 300 people, but, right, like, how are you having students interact with data and think about data as a part of the learning process? That, like, if in any way is trying to shift away from just purely, I'm going to pour this information into you or just throw it at you, however that works, and expect you to, like, memorize it and then still have some understanding of science. So, like, you know, many people, because I know a number of you, or I've met a number of you, many of you are scientists, right? So, like, how can you engage students in this thing that, like, we perhaps have come to, like, love and are committed to, right?
They just get a much richer understanding when they figure it out, and they're really happy about it.
The same is true for everybody.
To answer your question, Park, just in general, question for you is that in the longitudinal analysis of the biology scholars program, probably familiar with that on campus, surprisingly they found that the science efficacy, the capability, really didn't have as much of effect as you'd expect, right? But that the science identity was an enormous factor. That is, do you belong to this kind of community? And of course, the biology scholars program is this kind of community. So one suggestion would be, even if you don't change the course, if you can encourage the development of communities, however, that people feel that they belong to and begin to share and leverage the kind of stuff that you're doing. Maybe it's not done in the class, but you can set up a community to try to be a safe, wonderful place to talk about each course, and that's maybe a first step.
I think these are conversations that we need to continue to have because it's not easy, right? Question?
Can you contrast the amount of faculty effort and time that goes into developing a course with this approach versus a conventional course, and once the course is developed, can you contrast the faculty requirements to sustain the course?
So that's a very interesting question. I think there's a lot of effort anytime you're making major changes, right? That you have to create these tasks, test them out, and see how they work. However, now I'm going to reap the benefits of that, all right? Because I have these tasks that I know work pretty well.
I have to launch it for 5 minutes, and then I get to wander around the class, right, and talk to students and engage with them. So I actually think once it's developed, it becomes easier. It's the development phase that's hard, right? All right, well, if there are no other questions, thank you all so much. It was great being here.